Okay, there we go. Right, so no, don't be put off too much by astrophysics. So we don't know, and there's going to be a lot of equations here, I'm afraid, but it's really just for reference, and I'll talk rather to what they meant to mean. Um, so now what we're going to look at is I gave a sort of a morphological view of the universe. No, what are the radio sources? Now we're going to go a bit more into, okay, so why do they shine? Now, what's the physics behind them? And, and answer the important question, of course, is, so, why didn't the optical astronomers back in the day predict these things? Because there wasn't new physics, but there was new ways of looking at the universe. There were objects whose physics was known, perhaps, but they just weren't expected to be there. So, but what is astronomy? Well, what do you do with observational astronomy? You look up at the sky and you detect the signals that are coming down. And in particular in radio astronomy, what we do is we look at the intensity of radio waves that are coming from the cosmos. That's all these equations are saying. And the thing with the radio waves is they have a polarization associated with them. So we can talk about the total intensity of the radiation. So that's basically, you say, independent of polarization, how much energy is coming in. And then we say that there could be a linearly polarized component to that radiation. So basically, there's a polarization vector. And because it's basically is a vector, we need to describe it by two parameters. And those parameters are we call Q and U. And then there's circular polarization, where that vector is rotating around in the sky, and we call that V. So on the receptors, you'll see that there's an X and Y polarization. We measure the two polarizations, and we do that so that we can derive what we call here the Stokes parameter. So we can we can add the two polarizations together to get the total intensity. We can look at how much linear polarization there is, and we can look at how much circular polarization there is. But that depends on various things. So it obviously depends in position in the sky. So what I put in there, theta and phi. So the information, we point the telescope there, and we say, okay, that's what we're seeing from that direction over there. And we then look at a certain frequency, and we look over time. So we're looking at a very multidimensional thing. That we're trying to capture all of the information out of the signal that's coming to us as possible. We're saying, where is it coming from? Does it have some frequency dependence? Does it have a time dependence? And what is its polarization dependence? And those dependencies are all on each other. So if we're looking for pulsars, obviously then the time information is very important to us. If we're looking at redshifted galaxies, we're very interested in what frequency we're seeing the H1 line at, so dependent on those things. If we're wanting to make maps of things, then the position in the sky is important, so we can make an image. So that's basically what we're doing. And the equations to the right of the equal signs there is basically what our radio telescope does. Our radio telescope measures two polarizations, and talking about Meerkat and SKA, we detect linear polarization. So we detect an X polarization and a Y polarization. That's what comes into our receivers. Receiver has two outputs, an X and Y receiver. Then we've got a correlated beamformer and all of the other fancy stuff that comes behind, and that executes the mathematics that you see on the right-hand side. You take the E, and in this case here, what I'm interpreting E is the electric field of the electromagnetic wave coming in, and if you take the sum of the squares of the radiation coming in, that gives you the total polarization, and the other mathematical manipulations that you do there give you the other Stokes parameters. And that completely describes the sky. If you record that, then you've got all of the observational data that you can really extract from the sky, and then you pass it on to the astronomers and the astrophysicists, and they do their work. So that's sort of sort of shock and horror to start off with some maths, but then you go back to calm people down with a pretty picture. You stare at this for a while, and everything goes well. So that's what you see. And basically on that picture, what you're seeing is Stokes' I. You're seeing the total intensity. There's no attempt in this image to look at different polarization, but there's some very pretty images that show the polarization of these things. And And it's a continuum image. We're averaging over a lot of frequencies, and so there's no real frequency information in there either. So you get pretty pictures by doing this sort of thing. If we started looking at polarization, we would see some very interesting stuff that was correlated to those filamentary structures and things that tell us that magnetic fields are involved in some way. So there's a whole zoo and of different ways that we classify radio sources, and this is the kind of high-level one. We talk about thermal sources and non-thermal sources, and we'll see what we mean by that. And really what that means, it's thermal is more sort of sun-like, non-thermal more AGN-like. So more exciting is non-thermal. Thermal is kind of boring. Thermal is where things have been hanging around, they're doing their thing, they may be very hot or whatever, but they're not doing anything really exciting, they're not very dynamic. But when there's some dynamism involved, then things become non-thermal. A very important classification. So these aren't all mutually exclusive. These are all things you can mix and match these things as much as you like. We have continuum and spectral line sources. Continuum sources are broad spectrum sources, so there's no information in the frequency dependence of the signal. It's just a broad white noise type signal. Spectral line signal is like the H1 line. You have a very definite frequency where there's a signal, and then outside that frequency, no signal. And then there's the static signals, that carry on forever, and then transients. And transients kind of fall into two categories, subcategories of periodic and non-periodic. Periodic, things like pulsars; non-periodic, FRBs, where something goes bang in the night and doesn't happen again. And so that's largely the sort of classification that we can put all of our sources into. And different programs, though, look at different things. Now, again, some more shock and horror physics, but this is really underpin the thing. So Planck's law is something that came out of quantum mechanics, and obviously Planck was involved in this, and K there is Planck's constant. This equation, as you can see, its I is intensity. It says that the intensity of radiation from something which we'll call a black body follows this complicated looking formula at the top there. And this is what drove astronomy in the stellar era, that stars were black bodies. And so the intensity as a function of frequency of those black bodies followed that curve. But let me just see. Sorry, let's see what I've got up. Yeah. But we in the radio regime, we're working at low frequencies, and we don't like maths, and so we say, well, we're going to operate in the regime. So what you see there's this factor H, nu, and KT. So nu is frequency, T is temperature. H is a fundamental constant, very small, 10 to the minus 30 or so, and Boltzmann's constant is something times 10 to the minus 23. So they're both small numbers. But H nu, as I said earlier, is the energy of the photon. So and KT, if you in classical thermodynamics, is the energy contained, the thermal energy contained in a body. So if you've got a temperature T and you multiply it by Boltzmann's constant K, you end up with an energy. And so it's the amount of energy that's in your cup of coffee. If you take K times the temperature of your coffee, and H nu is the energy of the photons. So H nu over KT is a ratio, energy of photons divided by energy of the physical body. So it links together radiation and matter. So the KT part is matter, so hydrogen or something else, the temperature of that, and H nu is energy of the photons that are coming off of that matter. Now, we work in a regime of low frequencies, which generally means that H nu is much less than KT. This breaks down for very low temperatures, but no, it's pretty good. And if you do that, and then you do a Taylor expansion, then the E to the H nu over KT simplifies wonderfully to 1 plus H nu over KT. You plug that all in, and that leads you to a very, very much more simple formula for intensity at low frequencies, 2 KT over lambda squared, or equivalently KT nu squared over C squared. And you can see the watts of the units of intensity there, or watts per square meter per steradian per hertz, bit of a mouthful. So this is one of so this is just a kind of an important thing, strangely important thing. So this is no, this is physics at the top over here, and you end up with a bit of approximate physics. But then what we do is in radio astronomy we say not only do we not like maths, we also don't like long units. And saying watts per square meter per steradian per hertz all of the time is going to get us tongue-tied. So let's do a trick, and we use that, we invert that equation, and we define a new unit, and we will call it brightness temperature. And we get that brightness temperature just by solving that equation for T. And we say that TB is lambda squared over 2K times I nu. And that will have units of Kelvin just because of dimensional analysis. So what we'll do is, instead of talking about intensity with its horrible units, we will just do a conversion of units. Now, this is not physics. This is purely a convenience. We take an intensity in watts per square meter per steradian per hertz, we multiply it by lambda squared, and we divide it by 2K, and that will be our brightness temperature, which is in kelvins. Kelvins is much easier to say than watts per square meter per steradian per hertz. Nothing magic at all. It's just a definition. So when you hear astronomers talking about brightness temperature, they're talking about intensity in different units. That's all it is. That intensity does not have to come from a black body. It's just an intensity. You measure an intensity and you convert it into temperature. So if you look at the true Planck curves, you get these famous Planck curves, which have, and what you can see there is on the left at lower frequencies, this is a log-log plot, and you get a straight line. And that's what you expect because there's a frequency squared dependence. If you take the log of frequency squared, you get a slope of 2, and you work out that those things those straight lines on the left have a slope of 2. It's called the Rayleigh-Jeans approximation that we work there. And then as you go to higher frequencies, the spectrum turns over and goes down again. And that was the great thing about the Planck curves. What Planck saved physics from itself was if you just use classical physics, then what would happen is those curves would carry on going up to infinity to the right. And there was called the ultraviolet catastrophe, that classical physics basically said that any body of a certain temperature would emit an infinite amount of energy because it didn't turn over. But quantum mechanics came along, turned those curves over. So those are intensities as that we get from black bodies from different temperatures. And you can see the temperature ranges there. I've gone from 2.7 Kelvin, low temperatures, to higher temperatures. And you can see a general sort of trend here. One is, as the temperature gets higher, those curves go higher and higher. That means that if you've got some material, some body, if it gets hotter, it will give off more radiation across the band. Okay, it's kind of intuitive, but this tells us that what happens. It also says, as a body gets hotter, the peak in its emission will move to the right, will go to higher frequencies. So if something is hotter, it will emit more emission, and it will emit at higher frequencies. Now you might say, so what are these black bodies? And this is just showing, just one of those. If you have a cool black body at 2.7 Kelvin, the temperature of the universe, and you plot on a log block plot the frequency, its intensity as a function of frequency, you get the straight line with a slope of 2 because of the frequency squared dependence that we get there. Then it all turns over on the other side. You can see across normal range of frequencies, up to 10 gigahertz, the straight line is okay. Beyond 10 gigahertz, remember I said that radio astronomy goes all the way up to a terahertz. So when you get to a terahertz, we actually at frequencies where this approximation breaks down. And so you can't use it, but we still use the definition of brightness temperature nevertheless. As I said before, the universe itself is a perfect black body. So there we have, why am I talking about black bodies? Well, it turns out that in the universe, there are cosmological objects which do seem to behave like black bodies. Now, I should describe, and including the sun. It looks a little bit like a black body. It breaks with the black body. Now, what is this thing called a black body? And if you go to classical textbooks on physics, they all use different constructs for describing what a black body is. And it's basically what you can think of it is what most of the textbooks would say. You're in a cavity. You have a block of material, and you hollow out a cavity inside that material, and then you heat up that block to a certain temperature. Then, if you look at the radiation inside that cavity, then its spectrum will have this black body Planck curve. Why do you have to go to those lengths with this construct? What you've got to have is that the thing has to be in thermal equilibrium. Now you can see the word thermal coming in. This is where we talk about thermal emission. If the thing's in thermal equilibrium, it means that that body, the walls of that cavity are emitting the same radiation as they're absorbing. It means that the radiation is in complete equilibrium with the body around, no, with the material around it. Now you can see how that works for the universe, because we are in the universe. The energy can't escape from the universe. It's all in here, and the universe can become a black body. You take a star like the sun. You can say, okay, it can't really be a black body because it's not in a cavity. It's a blob of material, and it's actually radiating. So it's not reabsorbing the radiation that's giving off, which you would have in a cavity. So normally what the textbooks will do to say, okay, well, how do you measure the radiation in the cavity? You drill a tiny hole in the cavity, and then the radiation that comes out of that tiny hole will be a small fraction of the radiation in the cavity, so it's not going to disturb its spectrum. And that's, in fact, how people did measure black body radiation to start off with. If you're having a braai and you look at the coals, and you see the nice red coals, the radiation that's coming from inside the sort of the cavities between the briquettes, that's pretty good black body radiation, because the heat that's in there is bouncing around a bit before it comes out to you. So the coals and the radiation are in reasonable thermodynamic equilibrium. There's a bit of loss coming out. The same with the sun. The sun's a big blob of gas, and within the gas, the sun, radiation's bouncing around near the surface, and a bit of it's coming out and coming to us. But that is what that bit of leakage and that bit of non-equilibrium is what causes what you see in that yellow curve there, breaking with the black body curve. It's because there isn't a constant temperature. The sun, the outer layers of the sun cool down towards the outside. And so the radiation comes from a little way within the sun, from very hot gas, and then comes through some cooler gas on the way out. And so you've got it's not in equilibrium. And that's why you get the breaking with black bodies. So there are things. The moon is a very good black body. Venus is a very good black body. The solid objects are pretty good black bodies, because they have now thermalized. Now, the really magic thing about black body radiation is it doesn't care what the emission mechanism is. This is purely statistical physics. You've got something, that table, the floor, are pretty good black bodies, actually, radiating radio waves, because you're at 300 Kelvin. 300 Kelvin, if you look at my plot of black body curves, you'll see that peaks up in the radio. So there are examples of black bodies, but they tend to be quite boring things. They're just stars, planets, those sorts of things. But it's a fundamental thing that underpins a lot of physics and a lot of astrophysics, and was why people said that there were no radio sources in the sky. Because if everything was thermal physics, those sort of hot bodies or cool bodies or whatever bodies, if you use the Planck curve, it just went down to zero at low frequencies. And so you weren't going to see anything. So there's a whole lot of horrible maths here. But I'll try and describe it in best way I can. So we're used to thinking of astrophysical objects as being opaque objects. So the moon, the sun, they're solid objects. We can't see through them. Doors, windows, whatever, or not windows so much, but doors and they're opaque objects. They may radiate, but they're opaque. You can't see through them. So you see the thing. Okay, but a window you can see through. But you can sort of see the window as well if it's not being cleaned properly. But you can basically see through a window. What we look at in radio astronomy largely are objects which are not opaque. They are actually partially transparent. And that's and it's the same works in the optical as well, but it's particularly the case for radio sources. Now, one of the things as well, which I haven't put in here, but it's an important concept, is you'll see that we're using a unit of intensity. Intensity in either in brightness, temperature of Kelvin, but in watts per square meter per everything else. There's a big misinterpretation of what we mean by intensity. It's got a kind of our experience of the world, we use terms in strange ways sometimes, well, not the same way as a physicist would do. Intensity and flux are two different things. Intensity is how bright something is intrinsically. Flux is how much energy am I getting from that thing in total. Intensity does not, in free space, in the vacuum, where there's no attenuation, intensity is independent of distance. That means that the stars that we see in the sky are the same intensity as the sun, or even brighter. People say, well, that's nonsense because you can't see the stars, during the day. You can see the sun. The thing is, what we perceive with our eyes is actually flux. How much radiation are we getting across a range of directions? Our eyes don't have the resolving power, and the way that our brain treats things actually thinks about flux rather than intensity. And there's a very, very easy demonstration that intensity is independent of distance. I stand here and I look at that wall. It has a certain intensity. I walk towards that wall. It doesn't get brighter, stays the same. The sun doesn't get brighter as you go towards it. It'll kill you because the total emission that you're getting goes up as R squared, but its intensity stays the same. The intensity of the stars intrinsically is the same on Earth, well, above the atmosphere, as it is at the star. It's a thing to get your head around, but it's an important concept. We tend to consider flux rather, so that's the integration of intensity over a solid angle in the sky. So here when I talk about intensities, intensities are independent of distance. Now, but if you've now got a gas, say like the gas in this room even, the atmosphere, and you've got a ray of radiation, doesn't have to be radio, it can be anything, comes along over here like this, and it has an intensity. It comes off that wall and it passes through this room. If there was a vacuum in this room, it would pass through, the intensity would stay constant. But now you've got a material in this room, and the material in this room may do one of two things, or will do both things. It'll absorb the radiation. There could be physical processes that radiation gets absorbed by. There could also be processes in this gas which cause emission. There's a gas in here like the surface of the sun. It's emitting radiation. So in a vacuum, the intensity would stay constant. But now you've got a real material, and the material is both absorbing and emitting. So the absorption will make the intensity go down, and the emission will make the intensity go up. And that's what that top equation is saying. That the change in intensity with distance as you move along will decrease by an absorption coefficient kappa and will increase by an emission coefficient J, both frequency dependent. Everything in there is frequency dependent. And you can see the absorption is proportional to the instant intensity, because it's a fraction of the intensity will be reduced, whereas the emission is assumed to be independent of the stuff coming through. So that's a differential equation, and if you make simplifying assumptions, you can solve that differential equation. And I've got a picture later on which will, I think, describe this a little bit more in a little bit more understandable way. But a term that we'll hear is optical depth. And what the optical depth is the integral of the absorption coefficient over the distance that we come through here. And if the optical depth is small, we say that the thing is optically thin. If it's big, it's optically thick. And another, just a term that I want to introduce here is a thing we're going to call the source function, which is the ratio of the emission coefficient to the absorption coefficient. And don't worry about remembering all of these things. I'll remind us when we get back to them again. Now, this again This is just this is all maths. There's no physics here. This is all maths. We don't know what that cloud is. We don't know what that thing is. There's no physics being mentioned. We're not saying what's causing the emission. We're not saying what's causing the absorption. We're just tying them up into these coefficients. And then later on, we'll use physics to describe what those emissions and absorptions are going to be caused by. Now, what we but one of the outcomes of this equation, and I'll come back to this just now, is that if something is optically thick, now when we say it's optically thick, we're saying that that integral is large. And if you look at that integral, what it says is either that the absorption coefficient is very large, or the distance is very large, or both, which means that the emission coming through is going to be largely absorbed. If it's optically thin, then that emission passes through largely unscathed. And in the extreme, where something is optically thick, absolutely optically thick, it becomes opaque. And we don't see what's behind it. What was behind is completely absorbed. So that door is optically thick. I can't see what's on the other side. It's optically thick in the optical. Radio waves come passing straight through it. It's optically thin. So that's why there's a frequency dependence. Things have different optical depths and absorptions depending on where they are. So this is a kind of picture which supposedly describes that. So that S, as I said, is the ratio between the absorption and emission coefficients. And what we've got here is the intensity of radiation coming along and then going through some material which has a source function S. Now remember, the material has the source function because that source function depends on the absorption and the emission of that material. So it's a number. It's a very simplified thing. It's constant. It's a finite size. And then as the intensity, the light comes through that object, what that solution of that differential equation says is that the intensity of that light or that emission will tend towards the source function of that material exponentially. So if you've got a very bright object behind an object with a low source function, then that intensity will go down towards the lower source function. If you've got a low intensity source behind a higher source function material, the intensity will get bigger. Basically what it says is that hot objects, if you've got bright emission behind a cold object, it will get absorbed. If you have bright emission behind if you have hot stuff in front of a weak source, it will get amplified. Now, why all of this? Well, the thing is that most of the sources that we see, fortunately, in radio astronomy are optically thin. And it's a good thing and a bad thing. It's a good thing in that means that we can see far into the universe. So if we've got something here, a nebula here in the universe, it doesn't block out what's behind it. It just adds to what was behind it. So when we look out on a certain line of sight and we don't hit any opaque objects, we see everything along that line of sight, and it all adds up. That's the good thing. The bad thing is it's very confusing because you see everything and you have to then say, okay, what belongs to what? So I said earlier, George Smoot had to use my map of the galaxy to subtract out what he saw from the cosmic microwave background. Cosmic microwave background came along happily and then suddenly came through our galaxy. And the intensity that we were seeing from those directions was the intensity of the microwave background plus the galaxy. Now, if you want to know what the intensity of the microwave background is, you have to subtract out the galaxy. So it's a good and a bad thing, but optically thin things are good for us. So as I say, back in the day, optical people looked at stars, they were opaque, that was it. Done. Also, they were very small, tiny, so they didn't actually obscure each other. You could see each of the individual stars. You hardly ever find a star behind another star. So that's all a sort of a statistical description of where we're going. Now we eventually get to say, okay, so what is actually happening here? What's the physics? Why do we see radiation? Why do we see absorption? So we have an emission coefficient, we have an absorption coefficient. Why do we have those? What are the physical processes? And we'll start with continuum emission. Now, as I said before, continuum emission is where there's no particular strong spectral features. So a black body is a continuum source. It's got a shape, but it's a very smooth shape. So over frequency, there's a very predictable, very smooth distribution of emission. And these are the two main radio continuum emission things. One on the left is the thermal emission process. And what you have there is a hot gas like a nebula or a star, and the gas is hot enough that the electrons get stripped off of the gas. So you have a hydrogen atom, and the heat basically gets hot enough, and the electron says, I can't hang around here anymore, and leaves. And so you've got positrons, you've got the protons, positive, and you've got electrons, negative, and they're buzzing around in a plasma. So it's not actually atomic hydrogen anymore, it's a plasma. But every now and then, one of those electrons comes near a photon, and because of electrostatic attraction, gets deflected. Doesn't get caught, it just gets deflected. And that electron accelerates. It does a little curve. And as it does that little curve, it'll give off a radio photon. It's being accelerated. If you accelerate an electron, it gives off photons. And so you get those photons being given off. And that is what the emission mechanism is for when we look at nebula. So that when I showed the Orion Nebula earlier in the radio, that's what was happening here. You've got this hot gas. The electrons are being deflected by protons. The electrons are non-relativistic. They're not they're hot, but they're not going at relativistic speeds. And because there's no preferred direction here, there's no polarization. These electrons can be diverted in any direction. And so the signal is unpolarized. It contains all polarizations, in other words. The typical non-thermal emission mechanisms, again, is electrons, but now you involve a magnetic field. It's not an electrostatic force anymore. It's now a magnetic V cross B force. And you've got extremely high energetic electrons. So now these electrons are being excited by some process, like a black hole or a supernova explosion. So this is the things where there's a real kick. And this is now non-thermal because these things have not had a chance to thermalize. They haven't settled down. There's this continuous energy source that's giving them a big boost. And you've got these strong magnetic fields caused by pulsars or black holes or supernova remnant bubbles. These highly relativistic electrons, and they spiral around the magnetic field because of V cross B forces. And again, what you have is an electron which is accelerating, and an accelerating electron gives off photons. And so that's what we see, the emission that we see from AGN, from supernova remnants. It's this non-formal type. But now you've got a B field. You've got an electric field which has got a preferred direction. And those electrons are spinning around like this. And so depending on the direction that you look at this thing from, the photons from that emission are going to be polarized because they're going to be polarized perpendicular to the magnetic field. So you get polarized emission. So this is a thing. So synchrotron is what we mostly look at. Jupiter, going back to Jupiter again, is actually cyclotron. Cyclotron is where the electrons aren't relativistic. They're still fast, but they're going around in more sort of classical way in things. Again, some more equations here. So these are the equations which describe these things now. So what I introduce here, you can see the kappa and J. So these are the absorption coefficients and the emission coefficients that you expect for these two different types of emission. And you could go and plug those back into the equation of radiative transfer earlier. But the takeaway from this, though, is that this points out the fundamental differences between the two emission mechanisms. Okay, the one on the left is electrostatic. The one on the right is magnetic. On the left, the distribution of energies of the particles is Maxwellian. Now, the people who've done statistical physics will know what that means. It means that the particles have thermalized. The electrons basically are in equilibrium. They've been there for a long time, and they've got themselves an energy distribution that they're quite happy with over time. And that's why we call these thermal sources. On the right, the energy distribution of the particles, the electrons, is a power law. And that is because these electrons are constantly being injected by some power source. And so they don't thermalize. They basically have a fixed, they have a power spectrum with an energy spectrum, which is this power law spectrum. The physical processes are different. So the form of the equations is different for the absorption coefficient and the emission coefficient. And it turns out for the thermal sources that source function that we spoke about earlier is identical to the Planck function. And this is one of Kirchhoff's laws. So this is not Kirchhoff's circuit laws, this is Kirchhoff's thermodynamic law. And Kirchhoff's law in words is that if something absorbs, it emits. And if something emits, it absorbs. So its emission coefficient and its absorption coefficient is a constant. And it's one of these kind of contradictory or these counterintuitive things in physics. So if you want something to absorb radiation, you want it to be a good absorber, but it'll be a good emitter as well. So back in the day when you used to build power amplifiers for hi-fis, you would paint your heat sinks black because they would emit better being black. But everybody knows that black things absorb better, but they don't actually, but there's an imagine that they do. So to emit, you have to absorb. And this is where this equilibrium comes in. The thing absorbs and it emits at the same time. That doesn't hold for the non-thermal sources. So for the thermal sources, we see that that the temperature of the object is a driver in the emission. The absorption coefficient and therefore the emission coefficient is proportional to the density of the electrons squared. So the electrons are the things that are emitting or absorbing, and so we can get a handle on the square of the density of the electrons. It's got a temperature dependence and a frequency dependence of minus 2.1, as you can see there. On the non-thermal side, we see H. H is the magnetic field strength. So the intensity of radiation coming from a non-thermal source depends on the B field, the magnetic field. So if we make an observation of non-thermal emission, we can make some sort of get some understanding of the magnetic fields that are involved there. Anyway, so it's just mostly words I want to get out of that. So what happens now if you take all of that understanding now you've got and you plug that back into our radiative transfer equation. Now, if you look, sorry, just let me get back to this here. So if you look there, the absorption coefficient depends on frequency to the minus 2.1 for the thermal sources and frequency to well, it turns out that it's frequency to the minus. If you plug that value of gamma in there, I should have put this down, shouldn't I? I think it's minus 2.7 or something. So there's a different frequency dependence on for the absorption coefficients of the two of them. But in both cases, it's a negative exponent. So that means that at higher frequencies, the optical depth of these things goes down. So they become optically thin at high frequencies. They become optically thick at low frequencies. So if you look at at thermal and non-thermal sources over a range of frequencies, if you look at a black body, then it's optically thick. It's optically thick, and its intensity will go up with the Rayleigh-Jeans +2 slope forever. Well, if you look at a thermal source, it starts off with a +2 because that's where the black body the Rayleigh-Jeans approximation clicks in, but then it becomes optically thin, and the spectrum turns over and ends up with a slope of minus 0.1, and the source function for for non-thermal sources has a plus 2.5 frequency exponent, so it goes up slightly steeper than the thermal sources. Then it turns over and goes down at minus 0.7. So what does this say? Well, it says when you go out there and you make observations of radio sources and you make observations at different frequencies, by looking at the behavior of the intensity over frequency, I can identify whether that source is a black body source, an optically thick source, a thermal source, or a non-thermal source. We call the slope of these lines the spectral index, and so you'll hear that a lot. Radio astronomers love doing spectral indices maps. And they love Meerkat because Meerkat receivers have very wide bandwidths. Traditionally, radio telescopes had very narrow bandwidths. So when you went and made an observation, you would make an observation at a very small range of frequencies, and you couldn't determine a spectral index from that. So you would have to go and observe at 2 or 3 different frequencies, different receivers. Now, hardware, we have a whole suite of receivers so that we can measure sources at different frequencies. Meerkat, across the UHF band or the L band, you can do in-band spectral index determination because you've got a wide enough range of frequencies to be able to fit a straight line to the intensities at the different frequencies in one band. Yeah. So that's great. That's a great thing to be able to do. So this is one of our main determinants of how do you determine spectral, no, determine what a source is just by doing that. But that was in terms of intensity. As I said, what we do is we transform our intensities into brightness temperatures. And basically all that does is it takes those plots and skews them over, because it is just a mathematical transformation. There's a multiplication through by frequency to the -2. And we'll talk about brightness temperature. So a black body, its brightness temperature is its physical temperature. But for other thermal and non-thermal sources, it breaks from that. And so it's purely just a convention. But again, that's what we do. So we look up at the sky. And what does the sky brightness look like? What is the brightness temperature of the sky? So now I'm using the term brightness temperature rather than the intensity. And you look across a range of frequencies. And this is now just looking up at the sky with blurred eyes. So you're not looking at individual objects necessarily. You're just going, what do I see when I look up at the sky? And over frequency, what you see at low frequencies, you get a steep rise in emission. And it comes down and it flattens out, and then it builds up again on the other side. So what's happening there? On the left-hand side over here, what you're seeing is the optically thin synchrotron radiation, non-thermal radiation of our galaxy. So what you're seeing in this curve here is that -2.7 slope that you're seeing over there is optically thin non-thermal emission. So that's the galaxy. This is the galaxy that Carl Jansky saw. This is the galaxy that Carl Reber saw. And so at lower frequencies, the sky brightness just goes rocketing up because our own galaxy is so bright, and it goes falling off. Then towards the right, what you start seeing is our own atmosphere. Now, our atmosphere is a gas. It's got a physical temperature, and it absorbs radio waves. Not very much at gigahertz frequencies, but as you go to higher frequencies, water vapor and the greenhouse gases, what become greenhouse gases, start absorbing radio waves. And so because they absorb, the atmosphere also emits. So it absorbs radio waves, but it emits. So you get this kind of contradictory thing that even though it's absorbing radio waves, the radio sky gets brighter because we're seeing the atmosphere. And so you get these humps, which are mostly water vapor. And you get the sweet spot in the middle. So from a gigahertz upwards to about 10 gigahertz, that's the real sweet spot from the Earth's atmosphere. And then, of course, you've got the cosmic microwave background, 2.7 Kelvin everywhere. You can't get rid of that. So, that's what the sky looks like. So why is SK low and SK mid different? Why do we have different telescopes for mid and low? At low frequencies, the sky brightness is so high, the intrinsic sky brightness is so high, it doesn't make sense to build high fidelity radio receivers because the sky is so bright. The noise from the sky is so bright. On the other side, it does. And so mid, well, there's two reasons. One is that when you get to the mid frequencies, you really want to control the noise temperature of your telescope. The other is that the size of your receptor, your fundamental receptor, scales as wavelength. So as you go to higher frequencies, your dipole antenna gets smaller and smaller, which means its effective collecting area gets smaller, as we'll see in the next lecture. So you end up in a situation where you're using a tiny thing to look at the sky, but you need a bigger thing. You need a square kilometer. The only way you can get to a bigger aperture is to magnify that dipole by putting it in the focus of a dish. So you need a dish. But at low frequencies, the wavelengths are so long that the dipoles are quite big. So individual dipoles are quite big. They have quite a big collecting area. So it makes sense to have these two different kind of telescopes. So as I said before, you go look up at Orion. In the optical, you see the nebula. And in the radio, you see thermal emission. You see optically thin thermal gas, so-called H2 gas. H2, strange sort of old conventions. H2 means singularly ionized hydrogen. Of course, hydrogen can only be singular ionized because it's only got one electron. It can only lose one electron. H1 is non-ionized hydrogen, and we'll come back onto that. And we've seen the supernova remnants. So these are, these bubbles. And as I said before, it's a filamentary kind of emission that you're getting because what you're seeing is electrons spiraling around filaments of a magnetic field. And that's why you see a picture that looks like that. But also you can see straight through them as well. So if there was something behind, you would see it. We've seen this before as well, the old AGN. And well, what's happening here is you've got these very high energetic electrons. There's a magnetic field. There's an intergalactic magnetic field, which is there. There's magnetic fields everywhere. It's one of the key things that SKA talks about as well. There's cosmic magnetism. There's magnets everywhere in the universe. And one of the ways that we look at the magnets is to look at synchrotron radiation because it's polarized. And we can therefore determine the orientation of the magnetic field. So these jets are incredibly well, highly polarized. And also, I've plotted down on the bottom right there is the spectral index of the emission. And if you look at the slopes of those lines on this log-log plot, you'll see that they're of the order of minus 2.7, which is what you expect for synchrotron radiation. So we know that this is synchrotron radiation. So that's all continuum. Now, if we go to line emission all has to do with atoms. We need some quantum mechanics, and fortunately, most of the universe is hydrogen. The simplest atom there is. We understand very, very well, and we can understand the hydrogen atom as being a nucleus, a proton, with the electron buzzing around it. The electron goes into different energy orbits, and when it transitions between two of those orbits, it either absorbs or emits a photon, and the photon has an energy of the difference between those two orbits, energies of those orbits. This is very classical speak now, and therefore it has a very determined frequency. So you end up with very determined lines. Rydberg's formula for hydrogen is taught even, I think, at schools these days, and you can work out what the frequency of those lines. And if you go into some more complex physics, you can work out what the absorption coefficient of those lines are, and you can go back and plug those into the radiative transfer equations again. But you can see this, the absorption coefficient now has this f of frequency in it. It's the shape of the line. And so it shows that it is a spectral line. It actually has a shape as opposed to being just a continuum thing. Again, you can see it's proportional to the square of the density of the electrons and inversely proportional to the temperature. We won't worry about that too much. But the nice thing is that we now have line emission. It's in a narrow defined frequency range. Because of that, we can do all sorts of things. One of the things we can do is measure the temperature of the gas. We can measure the velocity of the gas because it's a spectral line. It can move up and down in frequency because of red and blue shift. And the plot on the bottom right there shows that we see these absorption lines from a whole lot of different atoms. So in there as well, I think there's helium and carbon. So it shows that there are other things out there. So this is one of the lines that we look at. But as I said in the last lecture, the really, really key important one is the H1 line, H1, because it's unionized hydrogen. It's just it's atomic, not molecular hydrogen. It's not H subscript 2. We don't get much H subscript 2 in the universe. It's the starlight dissociates hydrogen into atomic hydrogen. And what is that the proton and the electron have spins, and whether the spins are aligned or anti-aligned, there's a small difference in energy associated with those. That energy, when you plug it into E equals H nu, becomes 1.42 megahertz. 1420, sorry, megahertz, 1.42 gigahertz. So this is really, really a wonderful tool for looking at the universe. We've got the spectral line, the known frequency in the rest frame. If it's moving, we can measure its velocity. Because of its absorption coefficient over here, you can see that it has a dependence on NH. That means the column density of the hydrogen. That means that if we measure the intensity of the spectral line, we can measure the mass of the hydrogen. But and this is the wonderful thing about optically thin. We can only do this because it's optically thin. Because it's optically thin, we integrate over the path length through the hydrogen cloud. I can't measure the optical depth of that table. I can only see its surface. But something that's transparent or partially transparent, I can measure through. Yeah, that was the great thing about the equation of the radiative transfer equation. So we can measure the mass of hydrogen by integrating things. We can do other cool stuff as well, but in emission, we can measure the mass. But this plot over here also shows absorption. So if we have a bright source, a continuum source with a broad spectrum behind some hydrogen, as that intensity comes through the cold hydrogen now, so you've got a hot source behind a cold hydrogen, the cold hydrogen will cause absorption lines. No, and so you can use the background source to interrogate the hydrogen in the foreground. And so again, this is where we use the other people's sources to help us. And as I've said, I've spoken about this before. You look at the hydrogen, you can look at galaxies, you can get the dynamics, and a very simple formula. Once you've measured the intensity of the hydrogen, you can integrate that, and you actually just get a direct measure of how much hydrogen there is there, and you can see these tidal interactions and everything else between things. So there's not only atoms, there's molecules as well. And molecules, we have other quantum mechanical aspects to think about. It's not just the electron and electron shells. Because molecules have three-dimensional shapes, it makes sense to talk about rotation of the molecules. Quantum mechanics says that rotation has to be quantized. And so the molecule can go through different rotational states. And when it's doing that, it may absorb or emit photons, largely in the radio, a lot of them in the radio, mostly at higher frequencies. The molecules can only survive in areas where there's not a lot of UV radiation. So normal starlight will sort of dissociate them. So they normally lurk in dark clouds. They lurk in dust clouds where the UV can't get to them. But we get these ladders of transitions. We get combs of radio emission. And no, this is I've said there. We get all these molecules: water, ammonia, any number of alcohols, a lot of organic molecules, which is interesting because that gives us reason to believe that life is not that uncertain. That there is life somewhere else, because there's already a lot of organic molecules out there, and there's enough alcohol to keep them happy. So it's a good thing. So special amongst the molecules are the masers. Now we all know about lasers, but there's masers as well. And what happens here is that you've got a molecule, and you kick it up into a high state of excitement, and that you can do that mechanically. Basically, you have some gases got a temperature, molecules bump into each other, and it's like in rugby, you bump into somebody. These days you get blown up for it, but you spear tackle somebody into his shoulder, and he goes spinning off, and so his rotational energy goes up. So that's what happens between this sort of roughhouse of molecules. And then it'll go from that excited state down to what's called a pseudo-static state. And it'll lurk there for a while. And then a photon will come along and will sort of bump into that molecule. And if that photon has the same energy as the energy difference to the next lower energy level in that molecule, that photon will spontaneously cause that molecule to de-excite to the next lower level. Those two photons, so the initial photon comes through, the initial photon just passes by, it causes the other photon to happen, and they go off in unison afterwards, completely coherently. So one photon comes in, two go out, completely coherent, and they go on to the next atom, and you get a exponential buildup. And you end up with these maser sources. So there's the emission that comes out grows exponentially as you go through the cloud. It turns out, if you go back to the equation of radiative transfer, what it is it's a negative absorption coefficient. So rather than the emission coming in and dying out exponentially, it now grows exponentially. And these maser sources are the brightest things in the sky. But they're very, very specific, because those two, that photon coming in must be matched exactly to that energy level in that next molecule. Obviously, it's come from one of those molecules before, probably. That means, though, that those two atoms or molecules have to be traveling in the same direction. Otherwise, they'll have different rest frequencies. So you need to have these collimated columns of gas. And it might sound improbable, but we see these things, they do. And these things are incredibly bright. They're incredibly small because you have to have this chance alignment of all these molecules. They're incredibly polarized because this is completely coherent emission. and very narrow band. No, because by definition, these photons have the same frequency. So you get these very bright, narrow lines. Sharmila is our local maser expert. She's been studying methanol and OH maser lines. And these are great things, but you see these things on the other side of the universe. They really, really are bright. So that's a great thing. We've seen pulsars, and I've spoken quite a lot about pulsars already. The astrophysics of them is a little bit beyond me, so we won't go into that. But as I said before, we can use them as tools for doing relativity, which is a fun thing. But just to finish off, so and this has most application perhaps to pulsars, and that's why I've put it in here. So throughout the galaxy and throughout the universe, there's a lot of hydrogen, ionized hydrogen, H2. So ionized hydrogen, as I say, is a bit of a misnomer because it's not hydrogen, it's protons and electrons. And through the equation of radiative transfer, we see that the intensity of radiation coming through these ionized hydrogen clouds is going to be changed in some way. And so the first of the equations there is basically what we saw for thermal emission. The intensity as you come through an optically thin cloud is going to increase, and it's going to increase with a frequency dependence of minus 2.1. But there's this coefficient, which we call the emission coefficient, EM, which is the integral of the density of the electrons coming through. So what determines how much the intensity increases as we go through an H2 cloud depends on the square of the density of the electrons and the distance that you travel through the cloud. So the bigger clouds will cause more intensity increase until you get optically thick, and then it all turns over. But there are two other effects that we have as well. One is that the speed of light in an ionized in a plasma is not constant, is not c. It's not 3 times 10 to the minus 8 meters per second. It depends on the density of the electrons. So when light comes passing through a H2 region, it slows down. And it's what we call a dispersive medium. The speed of propagation through that cloud depends on frequency, and it depends on frequency to the minus 2. So at higher frequencies, the speed is pretty much close to the speed of light. As you go to lower frequencies, things slow down a lot. And again, it depends on a coefficient called what we call the DM, the dispersion measure. And the dispersion measure, I'll do the mathematics. I won't do the mathematics. I'll show you the mathematics just now, just to show this is where this is coming from. So what I've given it there, it's in terms of a delay. So it's a differential delay. So by how much more is that radiation slowed down by the cloud? And it goes as frequency to the minus 2, but proportional to this thing called the dispersion measure, which is the integral of the electron density, not the electron density squared, but the electron density. Not only that, if there's a magnetic field permeating through this H2 region, we get what's called rotation, polarization rotation. It's the plane of the polarization of the radiation coming through gets rotated. And that rotation is proportional to a coefficient, again, we call the rotation measure, which is the integral of the electric field, the density of the electrons and the perpendicular projection of the magnetic field line. So it depends on which way the magnetic field line is oriented to the line of direction of the radiation. And what that does is it means if you have polarized light coming in like this, it will go rotating around as it goes through whatever's in front of you until where you get it. And so that happens up in the through in the universe, or through the galaxy and other places, through these intervening clouds. But very importantly, also the Earth's ionosphere. So the ionosphere up there is a plasma, and it has a big, strong Earth's magnetic field, and so radio waves get rotated as they come down to us. So these are just the equations of this whole dispersion story, just to show you that this, this is based really, really on physics that everybody who has done physics should understand, and you end up with a formula for delta t, which is summarized in what I had earlier. Now this is very important, and this is a big thing in Meerkat, because that means when you look at a pulsar, the pulsar pulse doesn't arrive when you think it does, because that pulsar is out there, and on the way to us here, it has passed through a whole lot of plasma to get here. Fortunately, the plasma is optically thin, so we see the pulsar on the other side, but depending on frequency, the pulse will arrive at different times. So if you have a wide bandwidth receiver, you don't see the pulse, because across the bandwidth of that receiver, that pulse is dispersed. So that on the left-hand side there, you see, as a function of frequency, if you split the thing up into different frequency channels, you see that at the higher frequencies, the pulse is on the left, and as you go to the lower frequencies, the pulse goes later and later, eventually does a phase wrap, that the delay in the pulse is equal to the period of the pulse, and so it comes back round to the other side again and continues down. And that's a bad thing, because it means that your pulse is smeared out. So in order to do pulsar astronomy, that's why we'd have to take Fourier transforms of our signals to get them into frequency channels, and then we can de-disperse. We can take that out. First of all, from the shape of that curve, we know that it's got this frequency to the -2 just sort of characteristic. We can calculate what the dispersion measure is. We can then subtract it out, and we can line all those pulses back up again, and we can add them together the way they should be. More insidious, though, is scattering. What happens with scattering is that the intensity coming through gets diverted in direction. So that means that when you see a pulsar going through one of these clouds, the rays that you're seeing have come from different directions. They're being dispersed as they come through the medium. And of course, the dispersed rays have traveled further than the ones that have come straight through, and you get the scattering profile. And the trouble is we can't undo that. It also scales with frequency. So at lower frequencies, we end up with our pulses getting spread out, and at higher frequencies, we end up with our pulses becoming quite narrow. So you say, well, let's observe pulsars at low frequencies, at higher frequencies. It gets rid of both problems. The dispersion's much less, the scattering's much less. The trouble is that they're non-thermal sources. Their spectral indices are very steep and negative, which means at higher frequencies, they just drop in intensity. So that is the sort of the trade-off that you make in pulsars. At lower frequencies, the pulsars are much stronger, but they have these horrible intervening effects that come along. Faraday rotation, again, this is just the maths that goes with that, that the left and right circular polarized signals passing through a magnetized plasma travel at different speeds. The material is what we call birefringent. It has and go through all of this horrible maths, and what you end up with is that that you end up with this rotation measure over here, or this delta phi over here, delta psi, which is by how much is the magnetic field, the polarization angle of the radiation rotated. Now, this again is one man's data and another person's noise, and vice versa. So this is very useful. So if you've got a very strongly polarized source behind another source, in front of another object, you can use this Faraday rotation in order to determine what the magnetic field is in that object, in the intervening object. So if you've got a nice big strong quasar, big strong AGN in the far distance, a very strong point source, highly polarized in the background, and in the foreground you've got another galaxy. And that galaxy's got hydrogen, ionized hydrogen gas in it. You can look at the rotation of the polarization of that background source, and from that you can plug it in backwards into this equation, and you can say, I can work out what direction the magnetic field is, and also kind of what the strength of the magnetic field is as well. So it's one of these things where you're using some other source as a probe of the intervening material. It's sometimes sort of wrongly called tomography. So you've got bright background source. You don't care about the background source, but you look at how that source's radiation is changed either through dispersion or through Faraday rotation, and you can interpret what has happened, what is there in the intervening, background. But we'll see in another lecture, this is also a problem because it de-disperses, it depolarizes the sources. It doesn't always have a nice coherent rotation. It sort of rotates in sort of random ways, and then that gets rid of the rotation. Or it's the Earth's ionosphere, which introduces a rotation of the intrinsic polarization of the source that you're trying to look at. So you need to take that out. But that's another lecture. So yeah, that is pretty much my limit of my knowledge of radio astronomy. So I've just shown my ignorance to everybody here. Thank you very much.
Okay, thanks, Justin. We have gone a bit over, but we are in lunch. So I think if you want to ask questions, we can do that.
Thanks, Professor. This is fascinating. Just on the last bit where you said, we mentioned that you're basically using the or a sort of an assumed source absorbed through an optically thin thing in order to measure that thing. So the source, are we always sort of, what is the best assumed source? Sort of, is it always the radio, the cosmic radio background?
The background radio galaxies, because they're there, they're strong, they're polarized, there's lots of them, and if you go, the thing is, if you go to high frequencies and look at them, you get their intrinsic polarization, because at high frequencies, all of these measures go down because of the frequency dependence. So you can make an assumption, or if you do differential measurements as well, there's a whole science in it, but it's
your safest bet.
Yeah, no,
Thank you.
It's one of the big science topics of the SKA, this tomography. Yeah.